Hello guys, this is Paul McWhorter with TopTechBoy.com and we're here today with episode number 13 in our incredible new tutorial series where you're going to learn Fusion 360 or you're going to die trying. What I'm going to need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to you guys who are helping me out over at Patreon. It is your support and your encouragement that keeps this great content coming. You guys that are not helping out yet, take a look down in the description. There is a link over to my Patreon account. Think about hopping on over there and hooking a brother up. But enough of this shameless self-promotion. Let's talk about what I am going to teach you today. And what I'm going to teach you is I'm going to teach you how to create 3D printable involute gears. They're sometimes called spur gears, but spur gears or involute gears, and I'm going to teach you how to do that. And I really love this because since a child, I've been fascinated with geared mechanisms, and it's just really cool that I can design, and I can build meshed gears and meshed gearboxes using Fusion 360 and using a 3D printer. So I hope you guys are ready to go because I am really excited about getting this lesson going. And so let me switch over enough of this introductory nonsense, and let me switch over and let me see if I can get my Fusion 360 set up here. And I'll get out of your way. And then we are going to switch over to Fusion 360, and I'm going to show you how to design gears. But before I show you how to design gears, it's important for you to understand a few of the fundamentals of properly designed gears. And the way I can explain it is to just show you how you might think about doing some gears based on the skill set that you have right now. Now, based on the skill set that you have right now, you might try to do something like this. And you can see in this design, what I did was I drew a circle, I put a rectangle on the circle, I replicated the rectangle around the circle, and then I extruded it, and I get something that looks a lot like gears. The issue though is that these gears would not work at all in a real applications, and in fact they're kind of called Flintstone gears. Now what happens as these gear teeth engage and push each other around, the tip of one gear tooth drags across the tip of the other. It's a dragging motion. And what happens with that dragging motion? Very quickly, you are going to round those corners off of the gear tooth. You're going to begin to very quickly wear your gears down. The other thing that happens as you wear that gear tooth down, you're generating wear debris. You're generating mechanical little shreds and pieces of metal or pieces of plastic that are then going to, not only are you wearing down your gear tooth, but that debris is going to end up in other parts of your design, and it's going to cause even more problems. So the first thing that you're going to have is you're going to wear out your gear teeth. The second thing is the wear debris is going to cause problems for other parts of your design. And the third thing is that dragging motion is friction. And friction in a mechanical design generates inefficiency. You have losses of efficiency because of the friction and because of the wearing motion. And the fourth thing that's going to happen is that dragging is going to cause friction. That friction is going to cause heat, and you can overheat your gearbox because of all of that friction and all of the heat that results from friction. So this type of thing does not work very well at all. Now, what is the magic of an involute gear? Now, what I'm going to show you here is what an involute or a spur gear looks like, and what that looks like is this. And let's go to a top view so you can see the difference. So instead of these square gears, we have a very precise and very mathematically designed shape, and the purpose of that shape is to have no sliding surfaces. When these gear teeth engage and when they push each other, they roll off of each other. There is no sliding. They just magically roll off each other. And that is because of the precise mathematical relationship that is used in order to design the gear tooth. Now, unfortunately, the math behind this is very complex, and it would take me 3 or 4 lessons to explain it. And I think you're probably more interested in jumping in and designing. And so I'm going to show you a tool that you can use to design these where you don't have to understand all of the equations. Even though I love math and I love the equations, probably beyond the scope of what we should really go in these lessons. So what we're going to do is I'm going to show you how to do this, and what you what you can do is you can come over here to a new design. All right, and the thing is that there is a gear designer in Fusion 360. It's just that it is hidden, and so the way to find it, you can see that we're on solid. You come over to surface, you come to mesh, sheet metal, plastic, and you go to utilities. Then in utilities, you come down and you go to scripts and add-ins. Scripts and add-ins. And then you come up in the script menu, you need to come over to add-in menu. And if you go to add-ins, what you can see is there is a gear generator. There's one that's written in C++ and there's one written in Python. It doesn't matter which one you use. It would matter if you were going to go in and change the script or edit the program, which language you were the more comfortable in. But we're not going to be editing the script, so it doesn't really matter. So I'm just going to choose the C one, and then what you would do is you would come down and click Run. And if you click Run, what is going to happen is it'll pop up with a box, and that box is going to say that the Spur generator has been added to your Create menu. Now, I've already done that, so mine is already there, and so all I'm going to do is close out here. Now, if I come back to Solid, and I come here to Create, you come down here, and voila, you have a Spur gear generator. So let's click on that, and then it comes up with this menu, and you're going to just fill in some things here of the gear you want, and then it's going to go out and it's going to generate that gear for you, and it is going to be the Involute design that will give you only rolling motion. Pretty cool, huh? Now for me, what I wish that it let me specify an outside diameter and specify the number of teeth and then give me that gear. But it doesn't do it quite that simply, but I can explain to you how to fill this out to get what you want. Now, the first thing that you really want to think about is you want to think about the number of gear teeth, because the way a gear works is, like, let's say the first gear has 24 teeth, the second gear has 12 teeth. When you spin the first gear, the second gear will rotate at twice the speed because there's half as many gear teeth, and it will spin with half the torque. So you've doubled the speed and you've halved the torque. If you spin the small gear, the 12-tooth gear, you are going to half the speed and double the torque. So when you're making geared mechanism, you can either get more speed or you can get more torque, but you can't get more speed and more torque. All right, so it's sort of like the speed times the torque remains constant for each gear in your gearbox. And hopefully that makes sense. So this one we want 24 gear teeth. Now down here it shows you what the pitch diameter is going to be. Understand the pitch diameter is not the outside diameter of the gear. It's shown here, and it's kind of the diameter of the pitch, which would sort of be the midpoint of the base to the tip of the gear tooth. And that's important to remember, because you've got to not think that the gear diameter is the pitch diameter. That's kind of goes through the center of the gear teeth. Now, it's just, that's not hard, but you got to keep that in mind. So if I want 24 gear teeth, I'm going to end up with a pitch diameter of 304 millimeters. That is a huge gear, but I want a small gear with 24 teeth. So how do we do that? That gets into the module. And the module, you could think of it as a reference diameter of the gear divided by the number of gear teeth. So what does that mean? If I want a smaller diameter, I need to have a smaller number of teeth. And so you can kind of write the equation down and look at it. But what I can see is that if I want this kind of like about 10, if I want this, like 8 times smaller than this, what I could do is I could take the module, let's say I want it like roughly 10 times smaller than this. What I would do is, instead of having a module of 12.7, I could put a module of 3, and boom, now instead of being huge, the thing is about 72 millimeters, which would be about right for what I am looking at. Now, the other thing here is you can see that there's a pressure angle of 20. Pressure angle matters if you're doing a really high performance gearbox, but for what we are going to be printing in Fusion 360, we don't have to worry about that much, and so a pressure angle of 20 would be fine for us. Now, what is very intuitive and what we do want to set is how thick do we want our gears? Well, I want mine 15 millimeters thick, and now how big of a hole do you want in your gear? And similarly, I'm going to want 15 millimeters on my on my hole diameter. The only other thing that you have to look at is backlash. Now, if you have 0 backlash, that means that the gears perfectly mesh together where there's no like tolerance. And if we lived in a perfect world with perfect manufacturing equipment, maybe you could design something with 0 tolerance. But if you want a little tolerance in there, you put it in as backlash. And so for backlash, to get exactly the right backlash, you would need to do a couple of prints and kind of zero this in. But I can tell you, for a 3D printer, usually about 0.25 would be a good starting point. They will fit together and there won't be a whole lot of slop in it. Now, after you printed these, you might want to go in and tweak it a little bit and see if you could make something work good with a little bit less backlash. You kind of want a small backlash, but where the gear teeth very smoothly mesh together without kind of ending up jamming up, if that makes sense. So I think we got everything in there that we need. We're at 1515. It's going to be 72 millimeters, and we're going to have 24 teeth. And so I do that. I say okay, and boom, there is my beautiful, elegant 24 tooth Involute gear. Okay, now we can jump in and we can do the mating gear by coming up and saying create. And then what am I going to create? I am going to create a spur gear. And the neat thing is, it remembered my last settings. And this is a pro tip. When you have 2 mating gears, they need to have the same pressure angle, okay, and they need to have the same module, okay, the same pressure angle and the same module. But what can I set? I can set the number of teeth to 12. I am going to leave the backlash the same, and then still 15 thick and a 15 hole. That makes sense. One thing I didn't mention is the root fillet. The root fillet is how much rounding you're going to put. The root fillet radius is how much rounding you're going to put on the base of the tooth. So instead of just having it come down square, you're putting a little bit of a fillet there. And usually what they suggest is fine, so I'm not going to change that. I didn't change it on the last one, and I'm not going to change it here, so I'm going to say okay. And then let's come up to a top view. And what you can see is it put it sort of in the same place as the other one, so they're in the same location, but that's okay. We can move it. Let me go ahead and show you that fillet. You see, this is the root fillet here, and just how much rounding you want on the base of your gear teeth. All right, now you can see what it did is it put them in the same place, co-located. So we need to go ahead and kind of move those. And also I want to move them out of the way because I want to design my base at the origin. And so I can right mouse click and then I can move. And so right mouse click and move. Okay, what do I want to move? I'm going to move the outside one. And then guys, don't drag and drop. With Fusion 360, you've got to get out of the habit of dragging and dropping, because if I just came down and dragged and dropped, I very well could pull that gear off of the XY plane, and it could be floating above the XY plane a small amount. Now, if you float it above the XY plane, it will let you do that. And you can export an STL file, and you can import that STL file into Cura, and Cura will slice it. And then what happens when you try to print it? You're trying to print in mid-air, and you're going to have a horrible mess. So as you're designing in Fusion 360 for 3D printing, and really for everything, be deliberate in moving things. And what you can see is that if I have this selected for move, if I have this kind of coordinate axis selected for move, it gives me a coordinate axis, and I want to stay away from this Z arrow. I want to come over to the X or the Y arrow, and then I can move it because I am constrained to not move Z, and I am only moving that might be Y. And then I'm going to go ahead and get it plenty out of the way. And then I'll click OK. That one's out of the way. Now I need to get this one out of the way. So I'm going to move and copy. I'm going to select it. And then I'll move it down here with the X. And then up here with the Y. And get it plenty out of the way. And then say OK. Now you said, well, you weren't deliberate about position. Yeah, because I don't care right now. I'm just getting it out of the way. So that all looks very good. And now I'm going to come back to the top view, and now I'm going to design the base. And so to design the base, I'm going to need to do a sketch. And so I am going to create a sketch. And what I want is I want a base for this thing to sit on. Well, what do I want the base to be? A little bit larger than the gear. Now, the problem here is I can see a little remnant of the sketch for the gear still on here. I think like that's the 24. And so if you look under the Spur Gear 24 and you come down here and you look under sketches, you see that sketch is turned on. So I could turn it on or off. Okay, and then down here, similarly for the other gear tooth, this smaller gear, this is its pitch diameter, and that sketch is turned on. And I could turn that off, and I could turn that off if I wanted to get that sketch out of the way. Okay, but what do I want? That reference diameter, that pitch diameter, which is shown here, that's not the right diameter. It needs to be bigger than that. But what's the problem? I know the pitch diameter. If you click on it back behind me in the lower right, it's telling me that that's 72 millimeters. You need to remember that the diameter of the pitch is 72 millimeters. The radius would be half of that, which would be 36. We're going to need that later. But I don't have the outside diameter of the gear. And so before I start sketching, I need to get the outside diameter of that gear. And so the way I can do that is I can get it over here where you can see it better. I need to get my inspect tool, and I need to get measure. Okay, now what the measure wants is it wants my first point. So I'm going to come over here to the corner of the gear tooth, and I'm going to set that for my first point. Then it asks me for my second point. I'm going to come across and I'm going to select that as my second point. And then you can see that it is telling me that the outside diameter is 77.97. Well, now, how big should I make the base? Well, I would want it like a millimeter bigger, but I would want a millimeter on both sides, so I should make it 2 millimeters bigger. So instead of 77, let's call it 78, 77.97, let's call it 78. I want to make it 80 millimeters, okay? So that is going to be 80 millimeters for my circle here. So now I'm going to create a sketch. I'm going to create a sketch, There it is. Okay, I'm going to create it on the XY plane, and now I'm going to design my circle. So I'm going to get my circle, I'm going to come out, and then what was that? That was 77 became 78, and we want this to be 80. Did I do that right? And I am sorry, but I am going to check that just to make sure. So I am going to inspect again. I'm going to measure. I'm going to see, can I do it while the sketch is still on? I hope so. I want to go from there to there. And that is indeed 78 plus 2 is 80. I did that right. But I just didn't want to move forward without having that right. Okay, now that is going to be the base for this part. I need the base for the other part. But how far should our shafts be apart? This is the way you do it, and you've got to remember this because it will work perfectly. It will work perfectly every time. The way you figure it is it's the pitch radius of the first gear plus the pitch radius of the second gear is the distance between center points of your two hubs. You take the radius of the pitch radius of the first gear plus the pitch radius of the second gear. You add those two together, and that's how far apart your hubs should be. So what do I need to do? I need to go in and I need to look at my pitch radius. We remember that the big gear was 72. So I'm going to go ahead and finish this sketch because we need to calculate that. So I'm going to turn that sketch off. So where would that sketch be? It would be under sketches, and I'm going to turn it off. And then I'm going to turn the other two sketches on. One is already on, and this one. And these are going to show me, this is going to show me my pitch diameters. And so the way I could do that is I think I could hit D. No, I would have to edit it. What I can just do is I can just point at it and click, and then look down in the bottom right, and it tells me that this has a pitch diameter of 72. If the pitch diameter is 72, what would the pitch radius be? The pitch radius would be 36. And so we need to remember that number. And so the pitch radius is 36. Now we need to figure out the pitch radius of the other gear. The pitch diameter of that is 36. So the pitch diameter of the small one is 36. So the pitch radius would be half of that is 18. Now 18 plus 36 would be 54. 36 plus 18 is 54. But now what is the problem with using 54? You're not leaving any tolerance at all. And so I am going to put a tolerance of 0.25. And so what is the distance between the two hubs? What should it be? I'm going to make it 54.25. Now again, this is just based on experience. We could dial it in if we did a test print, but this is going to be our starting point. Okay, so now I have the information I need. So what can I do? I can come back to the sketch that I was working on. It's fully constrained, by the way. Get these things out of the way. So I'm coming back to the sketch that I'd started, and I'm going to edit that sketch. And now what am I going to do? I'm going to give myself a construction line. So I'm going to go get line. I'm going to come over, make it a construction line. I think I'll come across this way. I click on the origin, I come across, and then I want to come over 54.25 like that. Okay, now what do I want to do? 54.25, that is correct, I am sure. Now I need to do my smaller circle, and to do my smaller circle I need to go in and I need to inspect this to get its outside diameter. And so I'm going to inspect, measure. I'm going to come from this point. I want to come over to that point, okay, and it did not give me, it's like it didn't select the second point really. Let's see if I can get it there. So now this is 41.95. Okay, 41.95 would be 42. Okay, and 42 plus 2 would be 44. And so what I want to do is I want to make my next circle over here, I want to make it 44. And so I'm going to come here, I'm going to click there, and I'm going to make this 44 like that. Okay, and that I think looks good. I need to make it not a construction line, so I'll take this off, and then I will turn that back on. Now, why do those two circles overlap? Those two circles overlap because the gear teeth are going to overlap, right? The gear teeth are overlapping, and so that intersection of those two circles would be that area where the two gear teeth, the mating gear teeth, are going to overlap. Now let's go ahead and finish the base by drawing some lines. Guys, when I'm doing tangent lines, I like to not connect them to anything, and I still have that darn construction line turned on, so let me turn that off. Okay, it is off this time. Now I'm going to draw another line, but if I try to bring that, what is this nonsense? It keeps making these things construction lines. No, I don't want a construction line. No construction line. Okay, like that. I don't like to draw the lines touching the circles, because if I draw them that way, you can get all types of goofy constraints that you weren't expecting. So I like to manually add the constraints. And I start by making all 4 connection points tangent. So I want this line, I got that other one selected. So I got to select, unselect everything, and then come up to tangent. I want this line tangent to this circle. This line tangent to this circle. Now I want this line tangent to this circle, and this line tangent to this circle. So you can see that they're lined up right, but they aren't, they've got this excess stuff. So how do I fix that? It might be excess, it might be too short. I want the coincident tool. So I get the coincident tool, and I want this point. Man, sometimes Fusion 360 is hard to get the point. I got it. That point coincident with the circle. I want that point. That point coincident with that circle. Okay. Now, even though it looks like it's there, it's not. Like, let me show you. I'm going to make this point coincident with this circle. And look, I'm not fully constrained, even though everything is black and you think it should be. That's because this point, if we zoom in, this point is not coincident with the circle. And now, boom, look at that. Look at that. It is fully constrained, and it is the shape I want. Now I'm going to go in and kind of trim this, and I'm going to be careful to hopefully keep it fully locked when I do this. But I'm going to trim here. 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 I'm going to trim here like that. And one more, that one, and one more, that one. Okay. Now I've got rid of my internal solid lines. A construction line is okay to have internally, but that is there, and that all looks really good. That looks really good. Okay, so now we can start designing our post. And besides the post, I don't want the whole gear rubbing against the whole base, because if the whole gear is rubbing across the whole base, you have a very large rubbing area, and you're going to have more friction if you do that. So I want to have a little hub that comes up for it to sit on, and therefore it's not just sitting on the base. But the first thing I'm going to do is make the hub. So let's draw that circle, and the hub was what? Well, the hole was 15, and if I made the hub 15, that would work in a perfect world, but given our uncertainty in manufacturing, we have to leave a tolerance. And what I've found is For my printer, the tolerance of about 0.2 is good. So instead of making the hub 15, I need to make the hub what? About 14.8, like that. Okay, and now I need to do a hub here, so I'll get the circle again, I'll click, I'll come out how far? 14.8, like that. Now that's going to be the hub, but I also need that little ring for things to rub around, for that little ring for things to go around, and so I'm going to make another circle, and that circle, let's say we wanted 2 millimeters on each side, and so instead of 16, we would want to make this 20, and that would be 2 on one side, 2 on the other, and that looks about right. That looks good. We come over here and we'll do the same thing again, and we'll make that 20 like that, and that really looks good. I do not like to have dimensions labeled inside the body, even though it's okay. It's just, to me, easier to see and read if I bring my dimensions on out like this. Okay, so I like it where I can clearly see the dimensions and they're not all crowded inside. I am fully constrained. I am ready to go, so I'm going to say finish sketch. It turned the sketch off. I'll turn it back on. We come over here and we are ready to extrude. So the first thing I'll extrude is the base itself, and I want it 5 millimeters thick, so I'm going to select it, and then I am going to go up by 5 millimeters, and I'm going to say OK. Now the little ridge that I'm running on, it can just be up by like 1 millimeter. So what I'm going to do there is, I'm kind of not seeing my sketch. It keeps turning it off. I'll turn my sketch back on. This little ridge, I guess I should go ahead and say extrude. Okay, this little ridge, I want to raise how much? Well, if the base was 5 and I want to be 1 above it, I would raise that. I would extrude it by 6. Okay, now I can come over here and I can extrude again, and then I can say extrude this, but just to use, you didn't see that, did you? Okay, I can extrude this, but what I'm going to do is I'm going to do a technique that we learned earlier. I am going to extrude. I'm going to start at a plane. I've done that, and I'm going to extrude to an object, okay? And then I can extrude to the top of my little ridge over here, right there, and then boom. Why did I do that? Because now if I change this one, it will automatically change that one. And then that just makes editing a little bit easier later on. And so I think that looks really good. We almost have a base, but what do we still need to do? We need to extrude this and this. And I'm just going to extrude them at the same time. That's another way that we can do it. How far should we extrude this? Well, I'm 5. But it's going to ride on that little ring, so I'm 6, and then the gear is 15, so 6 and 15 is 21, but I want the hub to be a little bit higher up, so I'm going to add another millimeter, and I'm going to say 22. Now, if I put these gears on this base, what is going to happen? The top of the hub should extend above the top of the gear by 1 millimeter. Does that sound good? Boom, we have designed ourselves a 3D printable spur gear set. And what you guys' homework assignment is to just see if you can do it on your own. Now, maybe you've been following along with me in this lesson, but I'm not going to give you something new and totally different to do. But what I want you to do is go back and design this on your own without watching me, just to make sure that you've learned what I've shown and you can start doing these little bit more complicated things by yourself. Now, in next week's lesson, what I'm going to show you is how would we assemble this thing in our design software here. So next week, what I'm going to be talking to you about is design. What I'm going to be talking to you about is how to move an object, how to align an object, how to join an object, and how to, kind of move things around, because it's really not intuitive. And the difference between move, align, and join, it's very subtle. So we're going to take a lesson next week and we're going to build on this gear set, and then we're going to start doing a lot more complicated things. So your homework is to design this on your own, 3D print it, and then make a video of your homework solution on and post it on YouTube. In the description of your video, link back here. In the comments down below, link over to your homework solution. And I do look at every single homework assignment that you guys submit. And so really like looking at the work you're doing, and I encourage you to look at each other's lessons as well. And then what is great is if you guys have a 3D printer, print it. If you don't, follow along as best you can, or see if you can go to the library or someplace in your area where you can access a 3D printer. But if you at all can, print it. Show your model on your YouTube video as well. Now, I did print this, okay? I did print this, and you can see it here, and you can see it here, and it is just absolutely beautiful. Now, I need to talk to you a little bit about tolerances, and this is what you have to be careful of. Using those tolerances that I just showed you, the first time I tried to put this together, it was kind of tight. It was kind of tight, and you think, oh, my tolerances are too small. I need to put a bigger tolerance. But you got to be careful, because when you 3D print, sometimes that, like if I was 3D printing a post, sometimes that first level has a little bit wider at the bottom or a little bit wider at the top. Or if you have a hole, the hole is a little narrower on the very first level that goes down and on the top level. And so sometimes things seem tight, but it's just because of a tiny imperfection in the very top layer or a tiny imperfection in the very bottom layer. And sometimes it seems like they won't go together, but if you flip the thing over, it'll go together a little bit easier. And that's just because of you're putting the narrow side, the little imperfection narrow side of the gear up against the imperfection wide side of the hub, and it seems to go on one way and not go on the other. The solution is not to go increase the tolerances. That's not the solution, because if you do that, once you get it on there and it kind of knocks off that little bad spot, then you're going to have too much slop in your gears. And so you've got to kind of really start thinking about your tolerances, and don't go automatically. What you can do is you can kind of get a little file and try to just file that corner off of the tops of your hubs, and maybe just file that little ridge off on the gear. So like put your finger in there. On this side, I don't feel a ridge. On this side, which was what was printed against the build plate, I feel a little ridge. And therefore, this goes on really easy this way, but if I go this way, it feels kind of tight. Well, you can either just file that off with a little file, very small file, or you can just kind of work it. And if you work it around a little bit, it will loosen up. But if I put this on, look at that. It has that little gap that we put, that little millimeter gap. And then if I put this other one on, okay, it has that little millimeter gap, and look at that. What do you have? You have a great fidget toy. Putting them on, yeah, there, it's just perfect. What I would say is perfect tolerance. And then you can see that the gear teeth are meshing well, and this thing is just really, really working well. So that is your homework assignment. What we'll do next week is I'll show you how you can move things around and start assembling these components in Fusion 360. And then I'll show that in the context of going from just one gear driving another gear to how we can go in and start building things that would allow us to make a gearbox. And so we are going to be spending a little time designing these gears. Now, if you're not interested in gears, you still need to take these lessons, because what I am doing in these lessons is I'm teaching you new design skills, and I'm teaching you new parts of the menus and capabilities in Fusion 360. And even if you're not interested in gears, what you learn in these examples will build skills. And I'm always kind of like, do I make the lesson how to move a part, or do I make the lesson building a gearbox, and as part of building a gearbox I show you how to move things. So I like to really have my lessons based on little prototypes that we're building, but in those lessons, even if you're not interested in the prototype, I am teaching you the design skills that you need in order to master Fusion 360. Guys, I hope you're having as much fun taking these lessons as I am making them. If you enjoyed the lesson, give us a thumbs up. Also leave a comment down below. That helps me with the old YouTube juice. If you have not subscribed to the channel, subscribe. And when you do, ring that bell. And guys, I really appreciate you guys who are ordering your filament from my links below over at Amazon. Same price as if you went to Amazon directly, but ordering through my links, you get quality material and you help the channel out. And I know a lot of you guys are doing that, and I really appreciate it. Guys, share this with other lessons. Share this lesson with other people, because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.